Charles Osborne, 30-plus year member of SARA, having served as director, VP, president for multiple terms over the years. He's recently retired satellite communication systems engineer with 40-plus years of experience in specialties like antenna performance, verification, low noise amplifiers, synthesizers, up and down converters, link budget analysis, and test engineering. He also was technical director of a radio astronomy observatory and educational lab facility for 8 years. Today, he's just completed building a house. He's getting his 3.7 meter dish back up and running for hydrogen line and 8.4 gigahertz amateur deep space network listening. Okay, Charles, go ahead.
All right, let's see if I can find the share button. Things moved around when you...
Should be bottom.
Yeah,
bottom center.
All I see is my mute and stop video and more.
Go to more. Hopefully that does it.
Okay, share screen. Okay, there we go. All right, how about that?
Looks good.
Let's go to full screen. Well, it doesn't want to go to full screen. Are you seeing my full screen, or are you seeing just the
We're just seeing the standard
standard
view.
Yeah.
Yeah.
All right. Let's see. Slideshow. Yeah.
You go
I've
to
had
the
the same
left
problem.
from beginning. Just go to the left and click on from beginning.
Okay. Yeah, that got it. Okay, thanks, Wolfgang.
Yeah, that works. Oh, nice.
All right. Okay, what I'm going to talk about today is some comparisons I did between my 3.7 meter dish and the scope in a box, a little 1 meter dish. So let's see if this works. All right. Okay, so what I've got is a 3.7 meter carbon fiber dish that I happen to have a good mounting point for the scope in a box antenna right on the back side of my feed. And so what I was able to do is, let's see, can you see my pointer? Okay. All right. The two connections for the scope in a box and the feed on the big dish, I'm actually able to just switch the coax back and forth and go from the LNA feeding one to feeding the other. So all the losses and the noise figure of the LNA and everything should stay the same. And so that was what I was doing here, was being able to switch back and forth without too much trouble. Okay, and I also have a standard gain horn. So this is for 1.4 gigahertz, and it's 16 by 22 inch by 16 inch deep, and it's got about 16 dBi isotropic of gain. And so I was able to switch over to that for a measurement or two, just to see how the gain compared on the scope in a box dish to the standard gain horn, and it's very comparable. So the scope in a box is about 50%, well, the standard gain horn's 50% the aperture size of the scope in a box, but the gain was within tenths of a dB of the same. So that implies got a fairly low efficiency, maybe 25% out of the scope in a box, but we kind of expected that with the wrong frequency feed and everything. Okay, and doing a little bit of performance comparisons, I did a hot-cold measurement where I look up at the sky to get a cold reading, and I was just estimating 15 Kelvin, but with the scope in a box, there's a lot more to it. The 3.7 meter, you can exclude most of the trees and other things and actually point at a cold spot. But scope in a box has a lot more trouble excluding things around it because it's got a lot of spillover, and Alex will talk about that some when he does his presentation, how he tried to improve on that. So mine will be just very much a standard scope in a box look at things. Okay, I did sun noise measurement. Solar flux, always record that so you know how noisy the sun was for that measurement. And I got about 0.98 dB of sun noise versus 6.23 dB on the 3.7 meter. So a significant difference there, but really it's because of the signal to noise that the scope in a box is seeing a lot of other stuff that brings its noise floor up. And then I did another measurement later where I add a Nooelec LNA. It's an LNA that is indoors and kind of helps the noise figure of the RTL-SDR. So that improved things a little bit to where I was getting 2.23 dB of sun noise. And my 3.7 meter dish was also improved by that a little bit to 8.06 dB sun noise. So you can see from the Y factors that at the very bottom, that the 3.7 meter dish and the standard gain horn are very similar. So that system noise temperature is mostly defined by the fact that they have good side lobes. And then the scope in a box 1.2 dB is much less because its signal to noise is a little worse. Okay. Here's some pictures actually of what we see. This is at 0 degrees declination, and it's on the 19-degree right ascension, 19-hour right ascension point in the sky. So scope in a box, we get a couple of lumps here. We can tell there's maybe 3 different things that are going on at that point. But with 3.7 meter, we see a couple of good, well-defined, sharp emission points there. Also, and I'll talk about this a little later, we've got these little lines here, which are 1400 megahertz spurious signals that are probably from one of the computers here in the house. And so that kind of gives me a good marker. 1420.00 is right here. And it's hard to cancel that out because it changes a little bit as I change the angle on the dish. Okay, and this bottom chart here is slightly improved by the addition of an extra LNA. That's that Nooelec LNA. So just a small change there from the noise figure improvement from having that second stage indoors to help cancel out the coax loss. Okay, now the way I'm doing a lot of these measurements is with the Sawbird hydrogen LNA and moving that between the different antennas. And so the Sawbird, when I ran some tests on it, it has about anywhere from 0.52 to 0.62 dB noise figure and about 40 dB of gain. And that was, I've got a couple of Sawbirds, and so that seems to be pretty consistent. And then later I added the LNA, and that has about 16 dB of gain and 1 dB noise figure indoors. Okay, and I'm feeding these with bias tees. Here's the Nooelec LNA and the bias tee that I'm using to power it up. And there's a little more detail on that near the end of the presentation. So when I was doing these measurements, I kept coming up with some fairly high numbers for the scope in a box. I mean, I was up in the 800 or 900 Kelvin when I did the Y factor calculations. And on the 3.7 meter with just the Sawbird, I was at like 300 Kelvin. Adding the LNA brought that down significantly to 168 Kelvin. So that some of these measurements, you can see we're getting Y factors from hot to cold of about 4 dB of change. And so that's a good thing to shoot for in terms of proving that you have less than 160 Kelvin of noise temperature. Okay, and I wanted to run some tests on the Sawbird to see what the frequency response looked like. And I've got some Excel spreadsheets of that if people want to look over the data in more detail. But the graph at the bottom here shows the blue line is the gain versus frequency. And we see that the 3 dB bandwidth of the SAW filter shows up as being about 67 megahertz wide. So it's running from 1442 to 1375 megahertz. And then it drops quickly down to 30 dB down from 1344 to 112. Let's see. It's off the side where I can't see you. Yeah, 1456. Okay, and the noise figure of 0.6 dB equates to 43 Kelvin. So it's a very good LNA, especially for the price. And we can kind of see the noise figure here in this orange trace. So it goes down and stays flat around that 0.6 dB point. Pretty much the whole bandpass of the SAW filter. And then as the loss from the SAW filter increases, the noise figure follows that. So it goes up as the SAW filter goes down. So that's pretty much a flip of each other because of that added loss. And then I ran some tests on the Sawbird to see what the different voltage effects would be. And so across the bottom scale here, we've got 0 to 6 volts. And at the very bottom, the orange trace is the noise figure. And then above that is the gain. So we've got 40 dB of gain, basically down to about 3 volts, and then it starts to affect it. And the current is pretty much linear. So as you go up in voltage, the current is increasing. That's what this blue line is. So you can see it, it'll draw about 140 milliamps at or 130 at 5 volts. And as it goes down, it really doesn't have that much effect on the overall noise figure of the Sawbird. So you could run it at lower voltages, or if you have some loss in the coax from the voltage, it's probably not going to affect you until you get down to 3.5 volts on the Sawbird's performance. One thing that usually happens when I didn't really test this because it's a lot more complex test is as you go down in voltage and current, you're probably more susceptible to overload from spurs and signals nearby. So that's one thing that might happen if your voltage is a little bit low. Okay, and I always power the LNA outside on the coax because I basically think that's a better way to shield it from surges and other noise and stuff getting on that DC going into the to power the LNA. It also has a USB connector, and I would put the warning in here that if you power it by the USB connector, it also comes out the output, coaxial output. So whatever you hook that up to is going to see that voltage. So be careful with that. There's a lot of care that has to go in when you're powering things over the coax and have a chance of fighting between the RTL-SDR powering something or the LNA bias T powering. So essentially I was using the bias T's also to allow me to measure the currents and things and feed the voltages in myself rather than feeding the current through the RTL-SDR. That just seemed like a good way to cool it down a little bit so that it wouldn't have to source all that current through its USB connection as well. Okay, and I was impressed with the gain stability of these LNAs and the combination. Typically, I was seeing 0.2 to 0.3 dB of gain change when the temperature was doing a day-night variation from 70 degrees to up as high as 94 Fahrenheit outside. And so that's pretty impressive. I think there must be some compensation going on there to get that lucky. And of course, my RTL-SDR is indoors, as is the Nooelec LNA LNA when I'm using that. So that helps also. And my coax is underground. Coax has a temperature coefficient of its own, so the loss increases with the heat of the coax. So if it's sitting out in the yard, you might get a few tenths of dB if you've got a lot of coax just sitting on the ground getting hot. You may see some changes day to night caused by the coax itself. Okay, I've not done a lot of tests on this Nooelec LNA except at 1420. So I will mention that it's broadband. It doesn't have any filtering and it's fairly flat, as far as I know, up to a couple of gigahertz. So there is the possibility, if you don't have filtering ahead of the Nooelec LNA, that it would add to the problems because of out of band, being able to see Wi-Fi, GPS, other signals that might be in there. But in my case, I've got filtering from the Sawbird ahead of it, and so I didn't have as much issue with that. So just watch that kind of thing when you're adding the gain. It can make it more susceptible to to having overload problems. And also you're powering multiple things, so you can't really power the outdoor LNA through the LANA. It doesn't pass DC like some post amps do. So the LANA will have to have a separate bias T to feed its voltage in, and then you'll have to put another bias T after it to feed the voltage outdoors on the coax. So requires a little extra components there to be able to power all these things separately and block DC voltages from going back on the coax to the wrong thing. Okay, and I have a fair amount of coax loss. I have 15 dB of coax loss because I've got more than 100 feet of RG214 that goes underground out to the dish and then comes up through the wall of the house and up into the second story room where I'm at right now. So I needed to have a little extra gain to help overcome that. Okay, let's talk about noise and gain interactions. Basically, the noise temperature of the system indoors plus the coax loss gets divided down by the gain ahead of it. So let's say we have an RTL-SDR that has 7 dB of noise figure, and that's just the published spec. I think it may be higher. So that's 1165 Kelvin. The LANA has 16 dB of gain. So if we convert that 16 dB of gain into a factor, in other words, how much actual power gain does it have? It's a factor of 40 increase. So a lot of times when we're doing these calculations, you can convert to Kelvin and then use the gain factor number and divide things directly by that. So it makes the math a little easier to do. So if we take the RTL-SDR noise figure, or noise temperature, which is 1165, divide it by 40, it gives us 29 Kelvin of effect from that RTL-SDR noise that's added to the next stage. So the LANA's 1 dB noise figure, which converts to 75 Kelvin, gets added to that. So we end up with 104 Kelvin or 1.3 dB equivalent noise figure at the input of the LANA indoors. Now the coax loss is a passive, and so you can actually add that in dB directly. And so that 1.3 dB noise figure, equivalent noise figure, and the 15 dB of coax loss add together to give us 16.3 dB noise figure equivalent at the outdoor end of the coax. And if you convert that to temperature, it's 11,000 Kelvin. So the Sawbird is ahead of all this. It has 40 dB of gain, which is a factor of 10,000. And that divides that 11,000 Kelvin down to 1.1 Kelvin. So the 1.1 Kelvin is the effect of all that high noise figure following the Sawbird, yet it only has 1.1 Kelvin of effect. So there's very little leftover impact that you could measure in the temperature because of the Sawbird's 40 dB of gain. And so that's kind of the takeaway from this. I think a lot of people worry too much about the coax loss when the 40 dB of gain is really taking overwhelmingly reducing the effects of the losses. Okay, let's see. Going down through this. I think we went through all that. But if I didn't have the LNA in there, we would actually have a much bigger effect from all these noise figures indoors. So the RTL-SDR essentially will have a much bigger effect, but still it's only 5 Kelvin. If, however, we didn't have but 20 dB of gain out on the feed, things would be very different. It actually ends up being 500 Kelvin of effect on the overall noise temperature. So it goes from 5 Kelvin when you have 40 dB of gain out on the feed to 500 Kelvin if you only had 20 dB of gain. In my case, with all this coax loss in between the indoors and outdoors. Okay, in this past couple of weeks, in other words, what you see in the printed proceedings or the PDF was from about a month ago. And so I did a lot more tests using the LNA and the bias tees and things so that I could try to come up with a little bit more information for this presentation. So that's where the two differ a little bit in what we have presented here in terms of details. There's more details here in the that I came up with in the past couple of weeks. So as far as interference effects, the RTL-SDR seems to be the item that reaches some compression first. In other words, the effects seem to be affecting it. And so if you were doing a test and you can actually put an attenuator or some loss in between the RTL-SDR and the stages ahead of it and see an improvement in the performance, then that's telling you that there's probably some noise power overload going on. And I don't know if there's some gain settings that aren't obvious in the RTL-SDR that I might could reduce and be able to change that performance. So I haven't gone into it that much to see if there's not a sweet spot that things would work better with if it was adjusted differently. Okay, and I knew the question would come up, well, what about using 2 Sawbird LNAs in series? And so initially that was hard to do without getting overload. But then I found that I could add enough attenuation to actually get the 2 Sawbirds to work, one indoors, one outdoors. And the sign that you're getting some compression or some kind of overload was when I did the hot-cold test, and I only got, I think the Y factor dropped to 2 dB. And so that says I've really gone in the wrong direction by doing that. But by adding a little bit of attenuation, I was able to bring it out of compression. And so the 2 Sawbirds in series actually did work. But it's a very touchy adjustment. So you'd have to have, a collection of attenuators like I do to find the right attenuation, where if you add too much, it affects the noise figure. If you add too little, it runs into compression, and that affects the noise figure. So we definitely want to keep in that prime spot, and to do that, it's very tricky. So that might not be as as success-oriented of a test. And so I would recommend, you could use the Nooelec LNA as a second stage and almost always get good results if you have a fair amount of coax loss. But if you try to put two of the Sawbirds in series, that'll probably be too much. And it's a lot harder to get that combination to work. Okay, let's talk a little bit about SDR Sharp and the IF averaging application. What it does that's so important to us is if you look in this left-hand plot here, you actually see this three-pronged shape that shows up in the SDR Sharp screen. And what it's actually showing is there's a little bit of hydrogen right here. So almost imperceptible. And so that's kind of a zero signal, cold sky looking plot. You will see some hydrogen almost anywhere. Now, what the program does is when you put it through the IF averaging, then it takes and subtracts this signal from itself and gives you a flat line. So your IF averaging screen, when you turn it on, then will give you this nice picture on the right here. And you can see how difficult it would be to figure out in this center picture which one of these peaks is from the hydrogen and which is, what frequency they're on, because they're all sitting on this upslope of the shape that the FFT process creates. Now, another thing to notice here is that it's not level. And so there's a little bit of twist in these shapes. There's another one later that's much more balanced. And so I think some of the VSWR effects tend to cause these two peaks to not be at the same level, because you see a lot more twist in the scope in a box, which has like 7 dB of return loss, which is a pretty poor VSWR. But when I hook it up to the feed on the 3.7 meter, which has good VSWR, then I get a nice, more balanced plot most of the time. And so let's see, I think we've got all that. Yes. Go on to the next one. Okay, here's the screen, and this one on the right shows a nice, kind of a real low hydrogen signal depiction. And then, of course, when you do the IF average, you end up clicking this button here, or this check box, which creates this little screen on the left side of the picture. And so it's the, once you hit background down here, it does that normalization process that turns this into a flat line. Now, if you do the background like I do most of the time, I use the background function just pointing at a convenient spot in the sky. And sort of, if I pick a good spot that has very little hydrogen, then that flat line is almost the same as using absorber or something on the feed to try to do that normalization into as if you were pointing at trees or something. It's a little bit hard to do that on the scope in a box, because it sees the sky almost no matter where you're pointing, and it sees the ground almost no matter where you're pointing. And so it's a little tricky to get a normalization with it. Let's see. All right. Oh yeah, here's a trick that Alex told me, and this is worth passing along. Initially, this intermediate average box over here was set to 1,000, and the dynamic averaging would be up close to 1,000,000 or down to 400,000 traces. And it was very, it moved in big jumps. So a lot of these sliders they aren't very smooth sliders. They make big jumps. By using intermediate average down at lower levels, you'll see it on some of the next screens. I ran it on down to 10, and that made the dynamic averaging have more steps. And so I was able to control where this trace ended up on the screen a little bit better. And it also spread the signal out. In other words, it gave me a little bit more zoom in on the hydrogen line amplitude by doing that. Okay, and there is a lot of weird stuff that goes on in these in the program. So some of it may just be artifacts from something that was coded wrong in this IF average routine, because if you look on the side of the scale here, you probably can't see it easily on your screen, but it's 3 dB per division in this top portion and 2 dB per division in the middle right here, and then 3 dB in the bottom. And I don't think that really is nonlinear. I think it's just something that was coded wrong about how this scale gets created. So anyway, there's something that's going on there, and I didn't have a chance to really dig into it to figure out. I think it is linear. It's not quite as it's shown. So you can't just look at the side scale and try to guess what this peak value is, because the numbers don't make sense. Okay, and a lot of times things will move in 10 dB steps when you need much finer. So I hope we get a better program going for this that has nice smooth adjustments like SpectraView or New Radio or some of the other programs that are out there. But this is sort of what we've got to work with Scope in a Box, something that's all-in-one, can kind of thing. And there is a lot of touchy things here that you have to watch out for. Like if you want to stop the your captures, you can't hit stop in this other spot, and you can't hit pause at the top. Any of those 3 things will crash the program all the way back out to the desktop. At least that's been my consistent experience. And don't use reset. So when I want to stop the captures, I go in here into this number of files to save and just run it down to let's say I was on trace number 659. I would just manually go in and change this number to be 600, so that it essentially would say that it's finished. And the next time it finishes a measurement, it will then compare to that number and stop the captures. So that's a clean way of doing it without crashing the program and losing all your backgrounds and averaging and stuff. So I've been able to keep things running smoothly for days at a time by doing that, and multiple capture routines and changing where I'm pointing and which subdirectory I'm saving the file to. all without crashing the program or having to restart it. So that's kind of some of the touchy things you have to watch out for on this. Okay, and let's see, at the top here, this signal diagnostics application is right above IF average on my RTL-SDR screen. So SDR Sharp gives us this averaging routine, which integrates for 30 seconds. And so I always enable that and use this power block here as kind of a power meter for averaging or getting me an average power of what's on screen. And that seems to be pretty handy and seems to be pretty accurate. At least it performs in a useful manner. Let's see, we went through some of this, talking about the intermediate average and dynamic average. That gives me about a 90-second to 2-minute capture, which gives me good results on my 3.7 meter. I see changes that are happening in that two minutes, and get good smooth results. Okay, let's see, let's talk about the gain and level function here. Okay, these two sliders work in conjunction with one another to help set the position of the traces, and it gets everything to the maximum gain that you can get it, basically by moving this gain slowly to the right and this level portion slowly to the left. Usually it's near max, and the gain will be anywhere from 235 to 300 something. And so you move those back and forth to get to the traces to be in the right spot on screen. It's a bit tedious, but that's the best way that I've found to use it the way it's coded. Okay, most things are pretty small anyway. Center of the galaxy is less than 2.5 dB of change, even on the 3.7 meter, much less on the scope in a box. The sun, of course, you may get several dB. So when you're looking for these overload situations or where to set everything, doing a sun scan is a good way to figure out that everything is still in the linear range. If you get a good consistent number on that, then you're probably set correctly. Let's see, and I think I mentioned you could actually change some of these things. This file name portion, you can actually change that while you're capturing, and it'll just change the next saved file to be that new name. So if you're on the center of the galaxy, for instance, you could put that in the file name and sort of flag that in your file so that you knew where it was, or sun crossing, transit, whatever, or noise on, noise off for a test. So that's good to know.
Hey, Charles, 2-minute warning.
Okay, good.
2-minute warning.
All right. All right, I've had lots of trouble. I'm on my 4th RTL-SDR due to Microsoft updates and various things. So that's a warning to watch out for that. If it gets an update, it can kill a USB device. All right. Radio eyes. I use radio eyes to be able to see where these dead zones are that I can do the IF averaging background in. So that works pretty good. Look for something that's less than 18 Kelvin. Stellarium, I won't talk too much about that. It works great. I use it to figure out where I'm pointed, kind of as a viewfinder, zoom in on that telerad mode, and it gives a lot of the information about what you're looking at any given time. Gives you the galactic coordinates and stuff too. All right, and takeaway from this is you can actually set the scope in a box beam width and attempt to see what might be in the field of view. And I found that it was more like 40 by 50 degrees for scope in a box. So it's a pretty big chunk of the sky that you're averaging together. Okay, there's a couple of pictures from scope in a box versus 3.7 meter going through 100 Kelvin area. And I found the weaker areas of the galactic ridge have a lot more interesting stuff than galactic center, where everything looks kind of lumpy. Okay, and here's a couple more comparison shots. Some of the spurs I see once in a while, those are kind of transient. There's some of the devices that I used to do these tests. And there's the bias T and the Nooelec LNA part numbers. Okay, so we're down to questions. Good timing?
Good. We had one from Wolfgang about when you did the sun noise measurement, was this done about the same time in order to have the same solar flux? The sun has been quite variable recently.
Yeah, I was seeing quite a bit of difference. So I think I went from a day where it was 122 to 144. So yeah, that's worth noting anytime you're doing sun noise measurements to try to do those at the same time. But I didn't do the dish at the same exact solar flux on the same day. Okay.
All right. Anybody else have any other questions for Charles?
All right.
I don't see any more on that, and I don't hear anybody. Charles, excellent talk. Everybody's getting up to speed on scope in the box and its capabilities, and this really adds a lot of value.